Hello students, welcome to my class. This is Untitled. Today in this video we will discuss binary operation. Binary operation, this is the last topic of the chapter Relations and Functions of class 12 mathematics. Now to understand the concept of binary operation, we need to go back to our school mathematics. I think all of you know that we have four fundamental operations, that is the addition operation, the subtraction, the multiplication and the division operation. And all these operations, they have a special feature. That feature is that if we take two real numbers, A is a real number, B is another real number, then these operations, they associate another real number, A plus B, for addition, A minus B, or B minus A for subtraction, A into B for multiplication, and A divided by B with B not equal to 0 for division operations. Now see, it is interesting to note that these operations, they allow us to operate on two numbers only. That is, if we are to find out, say 2 plus 3 plus 4. Suppose I want to find out the sum of these three numbers, 2, 3 and 4. Now what I will do, I will take 2 at a time. Suppose I want to take this 2 plus 3 first. We see that the sum is here 5 plus 4 is equal to 9. That is the sum of these three numbers. Here see, we are taking three numbers, but we are working with taking two numbers. First we are taking 2 and 3, then we are taking 5 and 4. Similarly, in case of multiplication, even you notice that, suppose I want to find out 2 into 3 into 4. Here also I need to take two numbers at a time. First, suppose I want to take 3 into 4, which is 12. 2 into 12 is equal to 24. So this is the product of 2, 3 and 4. So from this we notice that these four operations, that is our addition, multiplication, subtraction and division, they allow us to operate by taking two numbers only. And since we are taking two numbers at a time, therefore these are referred to as binary operations. As you know that binary means two. Okay? Actually these four operations, these are some examples of binary operations for real numbers, and there are so many other binary operations, means we can generalize this concept of binary operation from this set of real numbers to any arbitrary set, and the binary operation will be referred to as star. Let's take the definition of binary operation. A binary operation star on a set A is a function star from A cross A to A. That is nothing but a function. I think you have already understood how we define a function. You are familiar with the concept of function. So therefore, now what we do? We define this binary operation star in terms of a function which is defined from the set A cross A, that is the domain will be the set A cross A with the codomain A. We write star A comma B is equal to A star B. Of course, this pair A comma B, this will come from the domain A cross A. So this is how we write. We denote star A comma B, that is an element from the domain A cross A. Okay. So star A comma B, that is equal to A star B. So this is how we denote this binary operation. Now let us have some examples. Again see, we go back to our school mathematics. We take the set of natural numbers. We take the set of natural numbers along with the operation plus, that is the addition operation. Now see, all of us know that sum of two natural numbers is again a natural number. Product of two natural numbers is again another natural number, but this is not always true, because if we take subtraction, if we take the subtraction operation, then we see that subtraction of two natural numbers is not always a natural number. And similarly is the case for your division, because if we take two natural numbers, then divide one by the other number, then the resulting number, it is sometimes a natural number and sometimes it is not a natural number. That is, in other words, in a very simple language, we can say that n, that is the set of natural numbers, is closed with respect to your addition than with respect to multiplication. But n is not closed with respect to subtraction and with respect to division. And now say that particular closure property has a relation with these binary operations. You see, n is closed with respect to addition. Now I will say that that particular addition operation is a function from n cross n to n. Let us verify that particular result here. We have taken n, the set of natural numbers, and the operation plus. Okay. Now say this is n cross n. And this set is n. I want to verify that plus is a function from n cross n to n. Okay, first we take suppose 1, 1 in our set n cross n. Now how we define this plus? Plus is defined as plus a, b, that is defined as a plus b. This is how we define plus. Plus a, b. A, b has been taken from the set n cross n, which is domain, and n is our codomain. So if I take an element a, b from our domain and operate with plus, it gives us value what? A plus b. Now say then 1, 1, this particular pair, it will have an image what? 1 plus 1 equals to 2. And it is important to note that 1, 1, this pair will not have any other image. So this point is important. 1, 1, this particular pair will have only one image, which is 2. This cannot have any other image other than this 2. Means image of 1, 1 is unique. Say I take 2, 3. In that case, we see that 2, 3 has image how much? 2 plus 3 is equal to 5. That is, in general, if I take an ordered pair a, b here, then this would give us a number a plus b in our codomain n. That is the condition for function. That is, every element in the domain must have a unique image in our codomain. That is satisfied here. So we have seen that plus is a function from n cross n to n. Or we may explain this as like this, that if we take two natural numbers, we may call like this: a belongs to n, b belongs to n. If a is a natural number, b is another natural number, then a plus b is again a natural number. This is nothing but our closure property, right? Now, therefore, since plus is a function from n cross n to n, therefore we call this plus a binary operation. Okay? Because the definition of this binary operation, this one star is a function from a cross a to a, it is satisfied by this particular operation plus. Therefore, plus is binary in n. Next, in place of this plus, if I take the multiplication operation, let us see whether multiplication, that is our so-called into is a function from n cross n to n or not. If we can verify that this into is a function from n cross n to n, then we are done. Then we can say that into is a binary operation in n. Let us see, we take n with operation multiplication. This will be our set n cross n. This is the set n, and how we define this into? Let us define into a comma b as a into b. This is how we define this into. Now say from this n cross n, okay, function is here into. Let us take 1 comma suppose 3. I want to take 1 comma 3 from the set n cross n. Following the definition, this one into a comma b is how much? This is nothing but a into b. So following this definition, what should be the image of this pair then 1 comma 3? This will have image 1 into 3, which is equal to 3, and we see that 3 belongs to the codomain n, right? 3 is again in n. Okay, let us take suppose 5 comma 4. We take one more example, 5 comma 4. Let us see what is the image of this 5 comma 4. What should be the image? Product 5 into 4, which is 20, and we see that 20 again belongs to n. That is, in general, we can generalize this idea. We can write in this way: if I take any pair a comma b from this set n cross n and find out the image, which is nothing but a into b, we see that ab again belongs to n. That is, every element in this set n cross n will have a unique image in n, showing that into or multiplication is a function from n cross n to n, and therefore this multiplication is binary in n. We may write like this, that is, if a is a natural number, b is a natural number, then their product a star b star is your what? A into b, which is ab, is again a natural number. Here star is taken as our multiplication. So why multiplication operation is binary on the set n. But now if I take the subtraction operation along with the set n, I want to take the subtraction operation. As we already know that the subtraction operation is not binary on n. So why here we will try to verify that subtraction cannot be a function from the set n cross n to the set n. Let us take n along with the subtraction operation. We define minus as minus a comma b is nothing but a minus b. Let us see whether it is a function or not. We take here n cross n. We take here n, and here we have taken minus a comma b as how? A minus b. Say, for example, I take here 1 comma 1. Now following this definition, what should be the image of 1 comma 1? This will have image 1 minus 1, which is 0, but this 0 is not in our codomain n. 0 does not belong to n. That is, this particular pair 1 comma 1 is not having image in n. So why? It contradicts the definition of a function, because for this minus to become a function, every element in n cross n must have unique image. But here we see that 1 comma 1 it does not have image. Therefore, minus operation is not binary, because that is not a function from n cross n to n. We may rewrite this example like suppose for since 1 belongs to n, 1 belongs to n, but 1 minus 1 is 0, does not belong to n. Therefore, we will say that this subtraction operation is not binary on the set n. So this is all about the subtraction operation in our set n. Next we take the division operation. Let us see how this division operation is not a function from n cross n to n. We already know that division operation is not binary on the set n. We take n along with this division operation and define this division by a divided by b. That is okay, a divided by b. Let us write like this: a divided by b. I will show that this division, that is not a function from n cross n to n. That is not a function from n cross n to n. Okay, what is the definition here? A comma B is nothing but A divided by B. So I take 1 comma 1 here. Then following this definition, it should have image how much? 1 divided by 1, which is 1. Of course 1 belongs to n. Image of 1 comma 1 is in n, which is the codomain. We see what will happen to this image if I take 1 comma 2. 1 comma 2, this will have image 1 divided by 2, which is half, but it does not belong to n. We see that 1 comma 2, this is one such pair that it does not have image in our set n. Therefore, this division operation, it cannot be a function from n cross n to n, and hence that is not a binary operation on the set n. How we will explain this? 1 belongs to n, 2 belongs to n, but 1 divided by 2, which is half, does not belong to n. Therefore, division is not binary on the set n. Therefore, we see that division is not binary on the set n. So, this is all about the set n, along with the operations addition, subtraction, division and multiplication and division. In the same way, we can verify that if we take the set of real numbers R, then plus is a function from R cross R to the set R. We can verify this result that plus is a function from R cross R to the set R. Similarly, minus, that is the subtraction, that is a function from R cross R to R. Multiplication is again a function from R cross R to R, but this is not true for the division operation. This division operation is not a function from R cross R to R. In other words, you see, in case of your plus operation, we know that if we take two real numbers, then their sum. Take two real numbers, then find out the sum. You will see that the sum is again a real number. Okay. Then for this subtraction also, if you take two real numbers, find out a minus b, you will see that a minus b is again a real number, and similar is the case for multiplication. Therefore, we say that plus, minus and into, these are three binary operations on the set R of real numbers. But let us see what will happen to this function if I take the operation plus. See here, the set is R cross R, the first set is R cross R, the second set is R. We define division A comma B, how? By A divided by B. So this is how we define this division. From this R cross R, we take a pair, order pair A comma B, and division A comma B, that is a, I need to check whether there is a function or not. So this is how we define this division. Suppose I want to take 1 comma 2 from R cross R, find out the image will be what? 1 divided by 2, that is half, and it is seen that half again belongs to R. This half is in our set R. Let us take, say, 2 comma root 5 from this R cross R, and then find out the image will be what? 2 divided by root 5, that is 2 divided by this one is again in R. So all these pairs, these two pairs will have images. But if I take suppose 2 comma 0 with the second element 0, let us see what should be the image. 2 divided by 0, 2 by 0. But as we know that 2 divided by 0 does not make sense in mathematics, therefore we cannot say that 2 by 0 is a real number. So in fact 2 comma 0 is not having image in our set R. Similarly, if I take suppose minus 3 comma 0, this will also have no image in the set R. Means any pair in R cross R with the second element 0 will not have any image in our set R, as we know that division by 0 does not make sense. Therefore, this is not a function from R cross R to the set R, and hence that is not a binary operation. Therefore, division is not a binary operation on R. Why it is not a binary operation on R? Because that is not a function from R cross R to R. Okay? Now say, I want to modify this set R. I want to make this division a binary operation on a modified set with some modification. So what should be done? Here we have seen that everything has been occurred due to this 0. Now if I exclude this 0 from the set of real numbers and I want to define a new set, suppose I want to define R star, that is the new set, defined in this way, R minus 0, means it contains all the real numbers excluding 0, that is it contains all the non-zero real numbers. Now in this set R star, if I take this division operation, we can notice that this will be a function from R star cross R star to the set R star again, because R star does not contain 0, so there will be no difficulty while taking this function, and we can notice in that case that division will be a function from R star cross R star to the set R star, thus showing that division is a binary operation on the set R star but not on the set R. So this is all about the set of real numbers R with the operations addition, subtraction, multiplication and division. Now I will take one more example to understand this binary operation. Suppose I want to take the set of natural numbers n along with a operation star. Suppose example, n here is the set of natural numbers. We have taken n, the set of natural numbers, and define star on n as star a comma b is nothing but a star b is equal to modulus a minus b. Now my aim is to check whether this is binary on n or not. Now say star is defined on n in this way, that is from n, if I take any two numbers, suppose 1 belongs to n, 2 belongs to n, these are two natural numbers, and I want to see what should be 1 star 2. Then following this definition, you see this is our definition, that a star b is what? Modulus of a minus b. Put the value here, 1 minus 2, modulus of minus 1, which is 1, is again in the set n. Therefore 1 star 2, that will have an image which is 1. But if I take here 1 star 1, suppose if I take here 1 star 1, then following this definition we see that this will have image modulus of 1 minus 1, which is modulus of 0 is equal to 0, but this 0 is not in the set n of natural numbers. That is such pairs, that is 1 comma 1, we may take one example 1 comma 1, or we may take 2 comma 2, 3 comma 3 and so on. All such pairs will not have image in n. Means, see here, this is our set n cross n, this is our set n. If I take 1 comma 1 here, and how we define this star? Star is defined as a star a comma b. It is defined as a star b. How? As modulus a minus b. So following this definition of star, 1 comma 1, this will have image 1 star 1, that is modulus of 1 minus 1, which is 0. 0 is not in the set n, that is 1 comma 1, this particular pair is not having image in the set n, thus that is not a function from n cross n to n. This star, as is given to us, this star, you see, this star is not a function from n cross n to the set n, thus showing that it is not a binary operation on the set n. It cannot be binary. I think you have understood why this is not binary. But if I slightly change this set, if I want to make this star binary on a particular set, on a given set, then let us see by taking z here. Okay? What do we do? Z is the set of integers. We are taking z, the set of integers, and star is defined on z in this way. Then we notice that on z, which is the set of integers, this will be binary. Because you see, we take two integers. A is an integer, B is an integer, therefore their difference is again an integer. This is a very fundamental result, that difference of two integers is again an integer. Now see, when I take modulus of this a minus b, that is again an integer, means always this pair, you see, from z cross z, this is the set z cross z, if I take a comma b here, then this pair is always having an image modulus a minus b in the set z. That is, if I take the set z of integers and define star on z by this way, then we see that star is a binary on z. Because why? Because star is a function from z cross z to z. So this is how we can verify whether a given operation is binary or not. You need to check simply one thing. Take two elements from the set on which the operation has been defined, right? So that will be your first step. What you will do, you will take two elements A and B from the set on which the star operation has been defined. Then you find out A star B. If you notice that A star B is again in the set Z or Z, whatever it may be, it may not be always Z on the set, then your conclusion will be that the operation is a binary operation. If for some pair you see that there is no image, then the operation is not binary. So this is the method of checking any operation whether it is binary on a particular set or not. Next we will discuss two important properties of binary operations, that are one is your commutative property and the second one is associative property. I think you all are familiar with these two properties, that is commutative and associative. Let us go back to our school mathematics. We know that 2 plus 3 is always equal to 3 plus 2. That is, we say that real numbers are commutative with respect to this operation addition. Real numbers are always commutative with respect to addition. Similarly, 2 into 3 is equal to what? 3 into 2. We say that with respect to multiplication, real numbers are commutative. But this commutative property is not satisfied for this minus operation. You see, 2 minus 3 is not equal to 3 minus 2. Similarly, 2 divided by 3 is not equal to 3 divided by 2. That is, an operation may be binary on a set, but it is not necessary that that is always a commutative operation. Means, for example, we know that minus means subtraction operation is a binary operation on the set of real numbers. But here we have seen that this subtraction operation does not satisfy this commutative property. So these are some examples of commutative property. Now, how can we define this commutative property for any binary operation star on a set A. Okay, let us take the definition now. Definition: a binary operation star on A is said to be commutative if A star B is equal to B star A for all A, B in A. Means whenever this is satisfied, irrespective of the values of A and B, if this is satisfied, then we will say that this operation star will become commutative operation. For example, once again you look at these examples. Here you see 2 plus 3 equals to 3 plus 2. And as you know that this result is always true for any two real numbers A and B. Means we can write what? We can write this one: A plus B is always equal to B plus A. Irrespective of all the values of A and B, always we have that A plus B equal to B plus A. Therefore, this plus is R is said to be commutative with respect to plus. Similarly, this result for multiplication is also true for all values of A and B we take. That is, for any two real numbers A and B, we can write A into B is equal to what? B into A. That is, the commutative property is satisfied by the set of real numbers. So this is how we define this commutative property. I will take some example, but after defining one more property which is known as associative property, let me once again take some example from our fundamental mathematics. That is, here you see 2 plus 3 plus 4, 2 plus 3 plus 4. That is a basic result. You need to change the position of the bracket. In the left hand side, we have given bracket here in the first two terms. In the right hand side, we have given bracket in the last two terms. So this property is known as what? The associative property. This is known as associative property. In fact, this is always true. A plus B for three real numbers A, B and C. We can write like this: A plus B plus C is equal to A plus B plus C. That is known as associative property. And what do we say? We say that the set of real numbers R is associative with respect to addition. That is, this is always satisfied. Irrespective of whatever be the values of A, B and C, you can publish, you can verify that this result is always true. It is always satisfied. That is, associative property is satisfied here. Similarly, if I look at the multiplication operation, we will notice that A, B into C is equal to A into BC. This is always satisfied. Whatever be the values of A, B and C, we can verify that this is always satisfied. A, B and C have to be some real numbers, so this is always satisfied. Therefore, the set of real numbers are that set of real numbers that is associative with respect to addition and with respect to multiplication. But that is not associative with respect to subtraction, and that is not associative with respect to division. Now, how can we define this associative property for this binary operation star? Let us take the definition here. Definition: a binary operation star on A is said to be associative. Is said to be associative if A star B star C, give bracket here, is equal to A star B star C for all A, B, C in the set A. So that is the requirement for this operation star to become associative. Now let us take an example. We will check whether that operation star is commutative or not, whether that is associative or not. So one example we take. Example, let star B an operation on R defined as star A comma B is equal to A star B, which is defined as A plus 2B. So we have taken an operation star on the set R of real numbers, and how we have defined star in this way. From R cross R, if I take a pair A comma B, then this will have image what? A star B. And how we define this star? That is a combination of plus and multiplication. You see A plus 2 into B. That is a combination of plus and multiplication. So this is how we have defined star. Now first thing, 3 points we need to verify here. First thing, whether star is binary or not. Binary or not. This point we will verify here, whether this star is binary or not. Number 2, the commutative property is satisfied or not. Commutative property is satisfied by star or not. And number 3, regarding the associative property, we will check whether this associative property is satisfied by star in R or not. So these 3 things will have to be verified for this star. Now, see here, if I take a real number, then take B another real number, we see that A star B. What is A star B? That is given to be what? A star B is here, A plus 2B. Write here A plus 2B, A plus 2B. See here, A is a real number, B is a real number. So sum of two real numbers, A real number, B is real number. Therefore what? 2B is a real number. And we know that sum of two real numbers is again a real number. So it is clear that this is always a real number. It is obvious that this sum A plus 2B is again a real number, irrespective of the values of A and B. You take any value of A and B, you will notice that A plus 2B will be always a real number. Therefore, what? Therefore, star is binary on R. So this part is done. We have verified that star is binary on R. I think you have understood, you have got the point how we can verify this star, whether star is binary on R or not. We have noticed that A star B equal to A plus 2B, which is always a real number. So thus star is binary on R. Next part is this one. We will check, this part is already done. The first part, star is binary or not, we have already verified that star is binary on R. The second part is, we need to check whether star is commutative or not. That part can be solved in 2 different ways. I will show you both the ways. First thing, A star B. A star B is what here? It is given that this is A plus 2B. Right? So this is given to us in the definition. Then what should be B star A? Using this definition, following this definition, will you find out B star A? Of course, that should be what? B plus 2A. In place of A, you put B. In place of B, you put A in the definition. So B plus 2 I said. And from these 2 values, it is clear. Therefore, A star B is not equal to B star A. We have seen that A plus 2B cannot be equal to B plus 2A. Thus, the condition for commutative property is not satisfied in this case, and so it is not commutative. And you may of course see, you have seen that this is not commutative, alright. But to establish that this is not commutative, if you wish, then you may give certain examples. Okay, let me give one more example also. You may approach in this way or in this way, it's up to you. Suppose 1 star 2. Use this definition. A star B is what? A plus 2B. Then what should be 1 star 2? 1 plus 2 into 2. 1 plus 4 is equal to 5. That is 1 star 2 is 5 here. Then you find out what? 2 star 1. You find out 2 star 1. It should be 2 plus 2 into 1. That is 2 plus 2, which is 4. And we have seen that 1 star 2 is not equal to 2 star 1. Thus, that is not commutative. So when I verify that this is not commutative, taking certain example, as you know that these are known as counter examples, so we are done. That is, the second part is done. The star is no longer a commutative operation. That is binary, but that is not commutative. And one thing you should keep in mind, that you may approach either in this way or in this way. It is not necessary to write down both these two methods. You choose any one, either this one or this one. Then we go to the last point. I will check whether it is associative or not. We will check whether the operation star is associative or not. This associative property, it can be checked in two ways. That is, first by taking A, B and C, or by taking counter example. Okay, let us take the first method. That is, we find out A star B star C. What is A star B? A plus 2B here. So it should be A plus 2B star C. Then see here, A star B is given as A plus 2B. So to find out this part, you compare this with this definition. The first A plus 2B part has to be taken as A, and this C, it has to be taken as your B. Okay? Then what should be the value here? A plus 2 into B. In place of A, we have put A plus 2B. In place of B, we have put C. That is following this definition. Value will be what? A plus 2B plus 2C. We have seen that this expression, that is A star B, inside this bracket, star C is nothing but A plus 2B plus 2C. Then I will try to find out another value, that is A star B star C, which is inside this bracket. Here also, this part will be obtained first. A star. What should be B star C? It should be what? B plus 2C, following the definition, given definition. Then A star, this whole part, you consider this B plus 2C as our B. Then what is the definition? A plus 2 into B. That is, in place of B, you put this expression B plus 2C. A plus 2 into B. A plus 2B plus 4C. We have seen that this one is not equal to this one. The first expression has value A plus 2B plus 2C. The second one has value A plus 2B plus 4C. Both values are not same. Therefore, A star B star C is not equal to A star B star C, thus showing that that is not associative. Okay? The operation star, though it is binary, but we have seen that that star is not associative. Of course, we may establish that star is not associative by taking certain example. Now we go to the example part, and you remember that you should not write both these two ways. You choose either this method or choose the method of taking certain example. Now next we will take certain example to prove that this star is not associative on R. Let us take this simple example. Suppose 1 star 2 star 3. I want to find out 1 star 2 star 3. 1 star 2, you remember this definition. You write down here, since A star B is A plus 2B, that is given to us. Then what should be 1 star 2? It should be what? 1 plus 2 into 2 star 3. It is obtained following the definition of A star B, which is A plus 2B. This one is what then? 1 plus 4, which is 5. 5 star 3. Again you see, value is 2 plus 5 plus 2 multiplied by 3. That is 5 plus 6, which is 11. This will have value 11. Next we find out the value of this one, 1 star 2 star 3. My objective, my aim is to check whether that is associative or not. So this expression has value 11. I will check whether this expression will give us value 11 or not. So this is your 1 star. 2 star 3 will be 2 plus A plus 2 into B. That is following the definition of A star B. A plus 2 into B. 1 star. You see here, this one is what? 2 plus 6. 2 plus 6 will give you what? 8. 1 star 8. And this would be 1A plus 2 into B. Following the definition of star, A plus 2 into B. That is 1 plus 16 is equal to 17. Look at these two values. One is 11 and the other is 17. These two are not same. Therefore, our conclusion is that 1 star 2 star 3, this is not equal to 1 star 2 star 3, thus proving that star is not associative here. Now dear students, once again you look at this question again. See here, star. Star was an operation and it is defined on the set R in this way. Now what we have done, we have completed 3 steps for this particular sum. In the first step, we have established that star is binary on R. So that part is done. We have established that star is binary. Now the thing is that whenever an operation is binary, it may or may not be commutative, or it may or may not be associative. It may be associative or may not be associative. For the second part, we have verified that star does not satisfy the requirement for commutative property by taking example also, or by taking A and B also, right? So star is not commutative here, and in the last part we have verified that star is not associative too. Star is not associative. So this is all about your binary operation. You can verify whether star is binary or not. You can verify whether star satisfies commutative property or not, or star satisfies associative property or not. Next, we go to the another important part of this binary operation, which is your identity and inverse of an element with respect to binary operation. To understand this concept of identity and inverse, we take example again from our school mathematics. You look at this example. 3 plus 0 is equal to 3 is equal to 0 plus 3. That is a very fundamental result, that 3 plus 0 equal to 3, which is 0 plus 3. 2 plus 0 is equal to 2 is equal to 0 plus 2. In fact, this is true for any real number. For any A belongs to R, we can write A plus 0 equal to A is equal to 0 plus A. Now see, I think you can remember, you can recall that this 0 is known as the identity with respect to plus. That is known as the additive identity, right? 3 plus 0 equal to 3 equal to 0 plus 3. 2 plus 0 equal to 2 equal to 0 plus 2. So this 0 is known as the additive identity in the set of real numbers. And if you take the multiplication operation, you see 2 into 1 is equal to 2, again equals to 1 into 2. Or 3 into 1 is equal to 3 is equal to 1 into 3. In fact, this is true for any A into 1 equal to A equal to 1 into A. Now, from this 1, that is known as the multiplicative identity. That is the identity in R which respects to the operation multiplication. That is, we have the idea of two identities, which is one is your additive identity and another is multiplicative identity. But unfortunately, in n, you see in n, in the set of natural numbers n, we don't have the additive identity. because we know that 0 is the additive identity, but this 0 does not belong to n. 0 does not belong to n. So why? N does not contain the additive identity which is 0, but R contains the additive identity. Similarly, N contains this multiplicative identity. As you know that 1 is the multiplicative identity, and in N you see 1 is the identity with respect to multiplication and 1 belongs to N. Means from this it is clear that for a binary operation we may or may not have the identity in the set. Sometimes we may have the identity, sometimes we may not have the identity. Now we shall try to define this identity in general for an arbitrary set A with respect to a binary operation star. So let us take the definition here. How can we define the identity with respect to star? Take the definition here. Definition. Let star be a binary operation on A. So we have taken an arbitrary set A, and on that set A we have defined a binary operation which is star. An element E belongs to A. Within bracket you write here if it exists. It may not exist always. Okay? So here I have written if it exists. An element E belongs to A is said to be the identity with respect to star if A star E is equal to E star A for all A belongs to A. Means whenever this is satisfied for all A belongs to A, we call this E, that is the notation to represent the identity. We call this E to be the identity in that set A with respect to star. So that is the formal definition of identity. Now if we compare this definition with our known results, that is, suppose here you see 2 plus 0 equal to 2 equal to 0 plus 2. See here, this is satisfied. I take the addition operation, I take the set of real numbers. We have seen that E is taking here value 0. Okay? And suppose 2 into 1 equal to 2 equal to 1 into 2. Here this is nothing but E. So this is always satisfied. So this is how we can define the identity in a set A with respect to an operation star, binary operation star. Next we will go to the concept of inverse of an element. And before going to the concept, before going to the definition part, let me once again take an example from our fundamental mathematics. See here, 2 plus minus 2 is equal to 0 equals to minus 2 plus 2. This is known to us. We know that 2 plus, while adding 2 and minus 2, it becomes 0 equals to minus 2 plus 2. And this is of course true for any real number A. That is, for any real number A, we can have A plus minus A equal to 0 equal to minus A plus A. And here see, this 0 is the additive identity. This is nothing but the additive identity. Right? So this is the additive identity, and we say that minus 2 is the additive inverse of 2. Similarly, 2 is the additive inverse of minus 2. Means when minus 2 is the inverse of 2 with respect to addition, we call that 2 is the inverse of minus 2 with respect to addition. So this is about additive inverse in the set of real numbers R. Let us have a look for multiplication as well. See here, 2 into half equal to 1, which is the multiplicative identity, equal to again half into 2. This 1 is nothing but the what? Multiplicative identity. This is the multiplicative identity, and this half is known as the multiplicative inverse, which is known to be the reciprocal of 2. This is known as the multiplicative inverse of 2. Or we can also say that inverse of half is 2 and inverse of 2 is half with respect to what? With respect to multiplication. So if I skip the term multiplication, this will not make sense, because inverse of 2 means with respect to what? If it is addition, then it is minus 2. If it is multiplication, then it is half. Okay? So this is how we can have, we already have this idea of inverse. Now let us formally define inverse of an element with respect to a binary operation. So let us take the definition here. Definition: an element, say A in A, is said to be invertible with inverse B. You see, this inverse has to be again in the set A, with inverse B with respect to the binary operation, with respect to the binary operation, suppose star, if A star B is equal to E is equal to B star A, where E belongs to A is the identity. So any element A from the set A that is said to be invertible, it may not be invertible, that is said to be invertible, with inverse B belongs to A with respect to binary operation star. If this is satisfied, you see A star B equal to E equal to B star A, where E is the identity. Now I want to compare this result with our known result, which is 2 plus minus 2 is equal to 0 is equal to minus 2 plus 2. See here, if I compare these two statements, this is your A, this one is B, this is the identity, this is again B, and this one is E. That is, this is already satisfied by this 2 plus minus 2 equal to 0 equal to minus 2 plus 2. So why we call this minus 2 as the inverse of 2 with respect to what? Addition. So this is simple example to compare with this definition. You may compare by taking suppose 2 into half equal to 1 equal to half into 2. You see here, if you compare this definition with this one, 2 into half equal to 1 equal to half into 2, you will notice that this one is A into B. A into B equal to E equal to B into A. A is here 2. This is A, this one is B, and this one is the identity equal to, again here it is B and here it is A. 1 is the multiplicative identity, as you know, and 0 is the additive identity, I think you know. So this is all about the inverse of an element in a set with respect to a binary operation star. Now the thing is that this identity and inverse, I have already stated that a set may or may not have the identity in the set with respect to binary operations. I take one example to explain this further. I take the set of natural numbers. Okay? One example. Let us take n set of natural numbers. N is the set of natural numbers, and I want to define one operation star on this set n by star A comma B is equal to A star B is nothing but LCM of A and B. So this is a binary operation on the set n. Why binary? Because you take two natural numbers. It is very simple to verify that it is a binary operation. You see, you take any two natural numbers, you find out the LCM. As you know that LCM of two natural numbers is again a natural number. Therefore, this is a binary operation on the set n. Now I will check whether it is commutative or not, whether it is associative or not, whether the inverse or identity exists with respect to star or not. First thing you see, first point is here, star is binary. Why binary? Because for any A and B from the set N, A star B gives you LCM of A and B, which is again a natural number. Why binary? Because for any A belongs to N, B belongs to N, A star B equals the LCM of A and B, which is again in N. This is the reason why this star is binary. Okay, the first part is done for you, that star is a binary operation on N. Next we check whether star is commutative or not. I want to give you one example. Suppose you find out 1 star 2. What should be 1 star 2? 1 star 2 means what? LCM of 1 and 2. And we know that 1 and 2, these two numbers will have the LCM 2. Okay? Similarly, if you find out 2 star 1, again LCM of 2 and 1 will be again 2. That is, I can generalize this idea of LCM. A star B is equal to B star A for all A comma B in N. We always have A star B equal to B star A, thus satisfying the definition of a commutative binary operation. Therefore, this will be commutative. And number 3, the third part. Third part is to check whether it is associative or not. This part you try at home, the associative part. Associative part. You please try at home. This verification is very simple. You take, you need to simply verify that A star B star C is equal to A star B star C. And as you know that here star has been defined in the form of LCM of A and B, so it is very simple to verify that star is associative here. Then I will try to find out the identity here with respect to the star operation. But maybe the identity if it exists. So what do we do? I assume that let E belongs to N be the identity. I assume that E is the identity. Then can I write like A star E equal to A equal to E star A for any A belongs to N? That is nothing but the definition of identity. Since E here is the identity we have taken, therefore this condition must be satisfied. Now what should be, you see here A star E is already equal to E star A, because I have already proved that this is what? Commutative. So instead of taking 2, I want to take any one. Suppose I take this one. A star E equal to A. Why I have skipped this last part? Because already we have seen that this is commutative. Star is commutative. Therefore, instead of taking A star E and E star A both, I have taken only one, the first one. A star E. What is A star E? LCM of A and E is A. So this is very important. What it really means. What do you mean by the LCM of A and E is A? As you know that LCM means what? Least common multiple. That is, A has to be a multiple of both these two numbers, and A should be the least of all those multiples. Then definitely both these two numbers will divide A. A already divides A. So why? We take what? Therefore, E divides A. This part is important. This part is important. Why E divides A? Because A is the LCM of, that is, A is a multiple. A is a multiple of both A and E. Therefore, E divides A. Right? E divides A, and you see, this is true for any natural number A. You remember that E is a fixed natural number, and that fixed natural number divides all the natural numbers. So our common sense says that this number, it should be 1. Therefore E equal to 1. Why 1? Because 1 is the only natural number which can divide any A, where A is any natural number. Therefore, from this conclusion, we can, from this discussion, we can make one conclusion, which is E equals to 1 here. That is 1 is the identity. Of course, we can verify. Already we have obtained the identity to be equal to 1, and we can of course verify that if I take the LCM of any natural number with this one, the LCM will be the number again. Means, for example, suppose 2 star A. I want to verify this result whether the definition of identity is satisfied by 1 or not. Let us see here. See, 1 star, suppose 2. Since this one is the identity here, so our definition says that 1 star 2 must be equal to 2. 1 star 2 is what? LCM of 1 and 2. What is the LCM? Of course 2. So 1 star 2 will give you 2. That is thus satisfying the definition of what? Identity. Okay. 1 star 3. Again you see, what is 1 star 3? LCM of 1 and 3, which is again 3. Thus we can verify that this one, identity is obtained as 1. This one satisfies the condition of identity. Therefore our conclusion is that here 1 is the identity. And for the last part, I will check whether the inverse exists or not. So how can I check that the inverse exists or not? The last part, let A belongs to N be an invertible element. We assume that A is an invertible element and B belongs to N, B its inverse. B its inverse with respect to what? Star. We assume that A is an invertible element and B is the inverse with respect to star. Of course, therefore, what should be A star B? From the definition of inverse, A star B has to be what? Identity, where A is the identity which is equal to B star A. Comma, E is 1 equal to the identity. Because already we have evaluated E to be equal to 1. Therefore, E equal to 1 is the identity. So, A star B equal to E equal to B star A. Now say, already we know that this is commutative. So, instead of taking these two, I will take the first one. Means A star B equal to, I put E equal to 1. Because see, since E equal to 1 here, already the identity is obtained equal to 1. Therefore, I have substituted the value of E, which is 1 here. What is A star B? A star B is nothing but LCM of A and B is equal to 1. Now, see, this is very important. When the LCM of two numbers is 1, our common sense says that when LCM of two numbers is equal to 1, we must have both the numbers equal to 1. A equal to B equal to 1. Otherwise, this is never possible. Is it clear? So this is possible. LCM of A and B equal to 1. This is possible only when we have A equal to B equal to 1. So from this, our conclusion is that A, this one being an invertible element, so A, that is 1 is the only invertible element with its inverse B, which is 1 again. Therefore, 1 is the only invertible element. 1 is the only invertible element with its inverse 1. That is, this one is B, this one A. Okay? Therefore, 1 that is A. Let me write as 1 that is A is the only invertible element which is inverse 1. So this is how we can check whether a binary operation is commutative or not, is associative or not, whether the inverse or identity or inverse exists or not. If it exists, how can we find out the identity, how can we find out the inverse, and so on. I think all of you have understood this discussion, these topics of binary operations, and we are almost done with the first chapter of class 12 mathematics. So dear students, we will meet once again in our second chapter, which is inverse trigonometric function. Till then, bye bye.